Happy Tuesday, you guys. I hope that you had a nice weekend and are ready to jump back into the swing of things here. I went ahead and I file transferred to you the slides to the PowerPoint that you guys are seeing up here on the screen, because I thought what might be nice is instead of copying all of that down, you could just write right on top of it. I'm having a little issue with my pen. It's not working. Give me a second, because I definitely need to be able to write on the screen today, because there's a lot of notes to show you. What a bummer. I'm going to stop the recording for just a second. Okay, so after a couple quick pen issues, here we go. We're going to start on 3.2 today. I want to go over with you solving trig equations. I want to make sure that you guys are understanding that section completely. It's very, very important as we build throughout the rest of Unit 3. So our essential question for today, which we're going to cover in great detail, is when solving trig equations, what's the main difference between when they give you a specific interval versus no interval? So it's going to mean something different, and you're going to see when we do a couple examples. If I give you a specific interval, that means something about the way that you write your answer. And if they don't give you an interval, then we write our answer in a different manner. So you'll see as we go along today. That's what I'm looking for in the essential question. So here's our first problem. Hi, Nicole. We are going to solve this. So go ahead and write it on your paper. And what's great about trig equations is that we have been solving equations for so long in Algebra 1 and Algebra 2 that we actually are going to solve this the exact same way, same steps. Our whole goal always is to know what x equals. This one's just a little more complicated, so not really a big deal. We're going to circle where my variable is and do the opposite of that -1 first. This kind of goes back to Algebra 1. Now we're going to get rid of what's still touching my variable. So I have this 1/3 out in front. So to get rid of the 1/3, we're going to multiply by the reciprocal. Whatever you do to one side, do to the other side. So I'm going to pause for a second. So far, do those first two steps make sense? Moving the 1, multiplying by the 3. Excellent. Okay, now I have tan squared x. Well, we don't want to know what the square is, so we learned, a long time ago as well, to get rid of something that's squared, we are going to square root both sides. So I'm going to get tangent x equals, now whenever we're solving for a variable, you're automatically going to make it a plus or minus because we're going to have two options. Whenever we have a square, that means you have two answers. That was just a little hint that I taught you guys a long time back, maybe even last year. Whenever you have a square, that means you're going to have two possible options. So what we need to do is we need to use our unit circle and find the places on my unit circle where tangent is plus or minus √3. So tangent, remember, is opposite over adjacent. So my opposite on a unit circle is your y. Your adjacent is your x. Smiley face, everybody with me? So far, so good? So let's go ahead and check out my unit circle, and let's see the spots on my unit circle where I'm going to get √3 when I'm comparing my y divided by my x. So y divided by x. So here's my y, 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 and here's how I'm looking at my unit circle. Our numerators are √3. Everybody agree? The bottom's a 1. So my numerators are √3, the bottom's a 1. So if I'm looking for y on top, that means I want a √3 on top. So if I'm looking at my y's, which one has a √3 on top? This one does. Let's circle it and let's see if it works. So y divided by x. Do we remember what to do at the bottom when it's divided by a fraction? It really is just multiply by the reciprocal. So look, I got √3. Everybody okay with how I did that? So again, since y was on top, and y was root 3, I was looking for which one could possibly have a root 3 in the numerator. So pi over 3 is one of my answers. Is there another spot on the unit circle where when I do y divided by x, I'm going to get a root 3 or a negative root 3? Let's check. So there was a root 3. I'm going to keep going. There's a root 3. So 2 pi over 3 is going to work. So this one also works because remember, if I were to show my work, y divided by x, this time it's just a negative, right? So root 3 over 2 times negative 2 over 1, I would just get negative root 3. That's okay. Remember, I could have a negative or a positive root 3. So that one's okay. Let's keep going around. Do I have any other places where my y could be a root 3? Here's one. Do I have any other places? Here's one. So I actually have 4 possible options. Oh, wait. Sorry, right here, where my y is a root 3. So I have 4 possible options as my answer. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Is everybody okay with how I have four possible solutions from my unit circle? Yes, no, maybe so? Okay, so I have 4 possible answers from my unit circle. But what we learned last week is, are there only 4 answers? No, there's infinitely many possibilities, right? Infinitely many. Because remember when we graph these crazy things, up, down, up, down, up, down, up, down, there's going to be lots of spots, along that curving graph where we have our solutions. So let's think about how we're going to write our final answer. So we said we had pi over 3, 4 pi over 3. We had 2 pi over 3, and we had 5 pi over 3. But those are not all my answers. These are just our reference points exactly, our reference points from our original unit circle. So if it says solve, that wants your all possible solutions. It's not giving us an interval. It's saying forever over the lifespan of this graph, where are your solutions? So the way that I'm going to write my answer is we add that plus 2 pi n. Plus 2 pi n. That means you're going to take your answer. Remember, 2 pi is 1 full revolution. So it's saying go to 4 pi over 3 and do 1 full revolution. That's going to be another answer. Do another full revolution. That's going to be another solution. So here's how we write our final answer. Right, like this. So how many solutions do I have? Don't say 4. There are infinitely many solutions. Because it just told me to solve. That means I have tons and tons and tons and tons and tons of answers. Yes, you have 4 main reference points, but those are not your only solutions. We have infinitely many solutions. Everybody okay with that first one? Okay, and just stop me, if you ever have a question. So we did our unit circle. Let's jump to this one. This time I'm changing it on you. This time I'm saying solve it, but I'm giving you a very specific interval to solve. On my unit circle, where is 0 to 2 pi? Right here, and 1 full revolution. Everybody okay with that interval? So if I tell you from 0 to 2 pi, they only want the solutions that fall in your first interval. Do you guys see the difference in how they worded the question? So for instance, let's come back here. If I changed my directions, because I just want us to practice, if I changed my directions and I said solve from 0 to 2 pi, if I asked you that question, solve from 0 to 2 pi, you would have had 4 solutions only. Those original 4 reference points. Can I get a smiley face if you see the difference? So if I give you an interval, you're going to have a set number of solutions. If I do not give you an interval, you're going to have infinitely many solutions. Hint, hint, that just might be our part of our essential question today. Okay, so let's go back to this example. This time I'm asking us to solve, but I'm asking us to solve on a very specific interval. So let's start with this one on the left. Can you guys type in for me what would be our first step to solve this equation? What would I need to do to it? I would need to subtract the 3. Excellent. Let's do the one on the right. So the one on the right, tan squared x minus 3, I would need to add 3. So we said in the last problem, when I have something that's squared, the way that I get rid of the square is by square rooting it. So let's go ahead and square root both sides. What happens in this first problem, though? What happens when we try and take the square root of a negative 3? Anybody? Anybody? What happens in your calculator if you type in square root of negative 3? It will say error, undefined, it will say any of those things. So this one, there's no solutions because you cannot take the square root of a negative. We're not able to. In Algebra 2, we talked about imaginary numbers, but that's not what we're working on here in Pre-Calc. So we just get a stop and we get to say there's no solutions to that one. That's kind of handy when that happens. But this one on the right will be just fine. So I get tan x equals plus or minus root 3. This is the exact problem that we just did. You guys see this one? It was tan x equals plus or minus square root of 3. So this is the one that we just did. My whole purpose of bringing up this problem again was, number one, to show you that if you take a square root of a negative, you get no solution. But then also, if I give it to you on an interval, you are just going to give me the solutions that fall within that range. So 0 to 2 pi is one full revolution on your circle. So for this particular problem, which we already did on the previous slide, we've got pi thirds, 4 pi thirds, sorry about that, 4 pi thirds, 2 pi over 3, and 5 pi over 3. So let's go over the key differences one more time. If I give you an interval, there is a set amount of solutions. If I do not give you an interval, there is an infinite amount of solutions. Okay, moving on. Here we go. So in this case, even before we start solving it, if I tell you that there's an interval, does that mean I'm going to have a set number of solutions or an infinite amount of solutions? What do you guys think? Set amount or infinite? Yep, there's going to be a set amount because it's within a given range. So let's solve this crazy thing. Let's move our minus 2 over to the other side. Let's divide by 4. Okay, there's 2 ways to solve it from here, so I'm thinking most of you guys would probably reduce your fraction, which is fine. We're still going to get the right answer. Let's square root both sides. Goes plus or minus. So on the top, square root of 1 is 1, and on the bottom, square root of 2 stays square root of 2. But if you remember back from earlier this semester and Algebra 2, we're not allowed to leave square roots in the denominator, because this right now is not an answer that you would see on your unit circle. On our unit circle, do we ever see square roots in the denominator? No. There's no place on the unit circle that has square roots in the denominator. So you have to do what's called rationalizing the denominator, which is where you multiply top and bottom by what you see in the bottom. So this will give me root 2, and then on the bottom, 2 times 2 is 4, but the square root of 4 is 2. This is an answer we see on our unit circle. Did you guys see how I did that last step? Questions about that? Not allowed to have square roots in the denominator. And we also know that's not correct because it doesn't occur on our unit circle. Okay, so now I have cosine. Oops, I should have taken my square there. So now I have cosine x equals plus or minus root 2 over 2. So we are going to look at our unit circle, and since it's cosine, this one's a little easier than tangent. I'm just looking for my x values. Where do I have an x value of plus or minus root 2? Let's take a peek. Where do I have an x value of plus or minus root 2 over 2? So here's one. Let's keep going around our circle. Here's one. Root 2 over 2, root 2 over 2. So I have 4 solutions this time. I have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. I only have 4 solutions. So let's add these to this problem. So I do have a set amount because they want me to only go around my unit circle one time only. So not infinitely many, I have a set amount of solutions. So again, this time my solutions are, let's just rewrite them one more time. Pi over 4, 7 pi over 4, 3 pi over 4, and 5 pi over 4. So hopefully you guys are keeping your unit circle very handy. If you need another copy of it, let me know and I can file transfer it at the end. But you are using the unit circle this entire time. Are there any questions about any steps up there on the screen? Okay, great. Let's move forward. So now we're going to get into some that have multiple secants or multiple tangents in there. The ones we've done previously just had one word tangent or one word cosine for us to solve. This one has a secant squared and a secant. Can you guys give me a green check mark when it's on your paper? And as you're writing, just so you know, I did lock the Illuminate room because what we like to tell students is that you need to get here on time, because would you pay for a movie and then walk in halfway through the movie? No, you'd wait for the next movie to start because you've already missed too much at that point. So it's going to be the same thing with these recordings. If you're going to be more than 5 minutes late, then just plan to watch the recording because you've just missed too much stuff at that point. Okay, so when I have a secant squared, a secant, and a plain old number, this is actually a quadratic formula. Like this. Ax squared plus bx plus c equals 0. It's just a quadratic that's hidden. So what we're going to do is we're going to move this 2 to the other side. So I'm going to have secant squared x minus secant x minus 2 equals 0. Is everybody okay with what I did so far? So far, so good? Okay. Watch what we're going to do. Let's take the secants out of the equation. Let's forget that they're there for a moment while we factor. Let's just call this first term x squared. Let's call this next term x. We are used to these problems. When we would factor, I need two numbers that multiply to a negative 2 but add to a negative 1. Can we think of two numbers that multiply to a negative 2 but add to a negative 1? Remember back from factoring quadratics? So a negative 2 times a positive 1. Let's see if that works. Negative 2 times a 1 is a negative 2? Yes. Negative 2 plus a 1 is a negative 1? Yes. So that's how I know that I factored it correctly. You could also use quadratic formula, but we just like to plain old factor it if we're able to. Now, let's stop right here. And if from before, if I asked you to solve this, do we remember how to solve once it's in factored form? I would set each parenthesis equal to 0 and solve. Is that coming back to us from a while ago? When you're given a quadratic, you put it into its factors like this, and then you would set each parenthesis equal to 0 and you would solve. So in this case, let's put the secant back in here. Instead of saying x, because we just said x to make it easier on ourselves, let's put in a secant x minus 2, a secant x plus 1. So all I had basically done was just changed my secant into an x, and now I'm going to put it back. So we are going to set each parenthesis equal to 0, and we're going to solve. Secant x minus 2 equals 0, and secant x plus 1 equals 0. So let's move our 2 to the other side. Secant x equals 2, and secant x equals negative 1. Do you guys remember what secant is? Secant is the inverse of which one? Which trig function? It's the inverse of, shove these in your notes, gotta know these. Good job, Josh. Yep, secant is the inverse of cosine. In other words, secant is the same as 1 over cosine. So watch what I'm going to do. Right now, I'm going to make it 2 over 1. I didn't change anything. So if cosine and secant are inverses of each other, I'm able to change it to a cosine by just doing the reciprocal. That's cool. Okay, and then over here, again, secant is the inverse of cosine, so I'm able to change it into a cosine by doing the inverse. But when we flip negative 1 over 1, what am I going to get still? Negative 1. Okay, so you guys should be practicing that step all the time. Know your inverses, and all that means is you're going to take it and you're going to do the reciprocal. So if secant means cosine, I took its solution and I just did the reciprocal. Secant is cosine in disguise. I just took it and did the reciprocal. Because these are spots on my graph that I can find. I'm looking for where cosine is 1/2 and where cosine is negative 1. So let's go back to our unit circle. Let's find where cosine is 1/2 and cosine is negative 1. Oops, I guess I didn't put one in here. Just moving my circles there. Okay, so where is cosine 1/2? Let's find it. Changing pen colors. Cosine is 1/2 right here, so at pi over 3. Where else is cosine 1/2? Let's keep looking. Around, 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 around. There's 1. Cosine's 1/2. So I have 2 solutions. And which was my other one? So I found 2 for where cosine's 1/2. How about where cosine is negative 1? Let's look. Cosine is negative 1 at pi. So since I'm asking you how many solutions are there from the interval including 0 to 2 pi, that means starting from 0, we're going to do 1 full revolution. So in this case, how many solutions do you guys see on my graph? There are 3. 1, 2, 3. 3 total solutions. Sorry, I'm trying to flip my papers here. So this first one, this one on the left down here, this one had solutions of pi over 3 and 5 pi over 3. The second one had a solution of pi. So when the question says solve on the interval, this whole interval ended up having 3 solutions. Is everybody okay with that answer now, how I got there? All right, fabulous. How are we doing so far? Are we hanging in there today? Is this making a little more sense, I hope? I know I would love to have our sessions on Monday, by the way, but Mondays were already booked with stuff. So if you guys ever have a quiz assigned for Monday and you want to wait and take it till after our Tuesday session, I'm totally fine with that. So don't think that you're pressured into taking your quiz early just because it's on the calendar. You may always wait. Let's try this one last problem here. So this one also says to solve. 3.2 is actually the whole entire lesson says solve. Now, before we start, answer this question for me. Is this one going to have a set amount of solutions or infinitely many? Can you type that in? Set amount of solutions or infinitely many? You guys are absolutely right. Infinitely many. And if I say why, because there's no interval, right? They're not restricting me. They're giving me no restrictions. They want me to keep going around that circle over and over and over again. What you guys might notice about this one that's different than the last one is, look, I have a square, I have a regular x, I have a regular number, so we should be thinking I need to use, the factoring thing we did last time for a quadratic, but here's what's different. This time I have cosine and sine in the same problem. Do you guys see how it's not the same trig function? Well, that's a problem. We need to get it to be the same trig function. So what they want you to remember this unit is one of your trig identities. So let's write this one down. I'm going to get my black pen for a minute. It's sine squared x plus cosine squared x equals 1. That's one of your trig identities. The reason that they love for you to memorize your trig identities is that we can substitute them into problems to help us simplify the problem a little bit. So when I'm looking at my equation that they're asking me to solve and I'm comparing it to my trig identity, the only part of my trig identity that I see down here is a cosine squared x. That's the only part that's the same. Do you guys agree with that? This one has a sine squared, that doesn't have a sine squared, so that's not helpful. The only part that I see that's the same is that it has a cosine squared x, and this one also has a cosine squared x. So here's what we're going to do. We're going to solve this trig identity to get cosine squared x by itself. So let's all move our sine squared x to the other side. So why am I doing this? I know you guys are not really asking me these questions. I'm just getting you to prompt you to think about things. The reason that we are doing this is because right now I am not able to solve this trig function because I have two different trig equations in it. I have a cosine, I have a sine. Can't solve it right now. I need to make them all match and get them to be all the same. So I'm going to use a trig identity to help me simplify. Everybody okay with how I solved for cosine squared x down here? I just subtracted sine squared x from both sides. Okay, so what we're going to do now is, if this is telling me that cosine squared x equals 1 minus sine squared x, think about this for a minute. If I told you cosine squared x equaled 2, couldn't I go to where I see cosine squared x and put in a 2? Right? That's what we're allowed to do. So if this is telling me cosine squared x equals 1 minus sine squared x, I can replace cosine squared x with this highlighted portion. We're allowed to substitute into each other. So let's write the rest of the problem straight underneath. So the 2 is going to stay the 2. The plus 3 is going to stay the plus 3, sine x minus 3. The rest of my problem stays exactly the same. The cosine squared x is going to become 1 minus sine squared x. I am substituting it in place. Are we okay with that? It makes more sense if you think about it being a number. Again, if I said cosine squared x equals 5, I could go to where I see cosine squared x and I could put in a 5. In this case, it's a little more complicated than a 5, but we're still just replacing it. And my reason for doing that is I want all of them to have the same trig function inside, because watch what's going to happen now. Let's distribute this 2. So I just factored through the 2. Next, I'm going to combine some like terms. So I have a 2 and a minus 3. Gives me a negative 1. Look what I have now. I have a sine squared, a sine, and a plain old number. This is just like we did on the last slide where we had to factor it. Now, before we factor something like this, we are used to our leading coefficient being a positive number. Remember that from whenever we would factor things, because I'm going to take this and I'm going to change it into these. But in order for us to factor, we are really used to when I have a positive leading coefficient. So what we're going to do here is we're just going to do one quick step to make it so that I have a positive leading coefficient. We're going to multiply through by a -1. So that's going to change it to a positive, a negative, and a positive. Okay, so why did we do that step? Because we always want our leading coefficient to be a positive before we factor it. Okay, if at this point it's still, it just takes some practice, I'm just going to move that down a little bit. We can replace these with x's. So think about this being 2x squared minus 3x plus 1. So I just changed sine squared x to x squared, sine x to x, because this we've been factoring since Algebra 2. We need two factors that multiply. Remember when a is not 1 though, you have to do the a times c, so 2 times 1, and then they still need to add to -3. So our factors that are going to work, I'm going to help us out, and then you'll be able to go back and practice this later. It would be 2x minus 1 and x minus 1. If you're totally stuck on how to factor, you can always come in and see me or let me know, and I can send you a recording that reminds you how to go from here to here. Or you could always use quadratic formula. You have lots of choices. So I'm almost done. Now let's just replace these x's with sine x. So this really says 2 sine x minus 1 and sine x minus 1 equals 0. This is as hard as it gets, which is why I'm ending with this one today. So let's solve these. Remember how we solve? We're going to set each one equal to 0. So sine x minus 1 equals 0. So we're going to add the 1 over. So I need to know where sine of x equals 1. We'll look on a unit circle in just a minute. And then this one over here, 2 sine x minus 1 equals 0. So we're going to add the 1. So it's going to give me a positive 1. And then last step, we will divide by the 2. So look at where I'm looking for on my graph, on my unit circle. I need to know where sine x equals 1/2 and where sine equals 1. When I find those spots, those are going to be my solutions. But remember, since it did not give me an interval, I'm going to have infinitely many solutions. So let's try this together. Let's go to a unit circle. I need to know where sine gives me 1/2 and where sine gives me 1. So let's take a peek. Okay, so let's peek. Where does sine give me a 1/2? Remember, sine is your opposite over hypotenuse. So you're looking for your y value. So here my y value is 1/2. Here my y value is 1/2. And then our other answer was, where does sine equal 1? Right here. So solution, solution, solution. Pi over 6, pi halves, 5 pi over 6. You guys okay with how I found those on my graph? Okay, it just goes back to what it was asking us for. It was asking me, where does sine x equal 1/2? So here and here. And then where did our sine x equal 1? And that's right here. But how am I going to write my solutions? Oops, going to the end. Oops, there we go. So how am I going to write my solutions? I had pi over 6, 5 pi over 6, and pi halves. If you write your answer like this, that's showing me that there's 3 solutions. So that's not quite right. We're missing the little last piece of the puzzle. Good job, Dakota. So this means infinitely many again because I did not give you a range. So we're going to just add that little last piece, plus 2 pi n, plus 2 pi n, plus 2 pi n. So it's a big deal if I give you an interval versus I do not give you an interval. It means I have a set number of solutions or I have infinitely many solutions. So let me just remind you of our essential question for today, which we just answered 2 seconds ago. When solving trig equations, what is the main difference between them giving you a specific interval versus no interval? So just tell me about what it means about your answers in the drop box, and we're going to call it good. All right, I'm glad that my pen started working. Yay, because again, like I just showed you, I had to be writing on the screen today. There was no way I could get through today's session with just a mouse. So thanks, guys. I hope that you have a great rest of your week, and I will see you back here on Tuesday.